Hello, there are 3 videos to watch today. I hope each one is just as good as the last, if not better. So we're polishing off this chapter, which I think is chapter 9. And so a lot of this should be pretty easy / revision / whatever. So first one is just thinking about rates a bit more. So we've got a function, it's defined, whatever, it's just a normal fx, you know. Here's a, here's b, here's fx. So the function is clearly defined between a and b. And we say that the function is increasing throughout the whole interval if, and this one probably just is, if I draw a not straight line, very nice, if every value of fa is smaller than fb as for any b bigger than a. So in other words, it's always going up. Every sequential value of x gives a higher value of y, not the same value. So notice it's not less than or equal to. So examples of functions that satisfy that might be just a standard straight line for any value of a and b, or a parabola for any value where a is something bigger than the turning point. So if this is 1, if a is greater than or equal to 1, this will work. And you know, you might also think about, well, cubic, like that works almost everywhere. Oh no, it actually works everywhere, yep. But this doesn't, right? You have to be over here or back here for it to work. And then we say it's decreasing if the opposite is true. So in my first example, this section is decreasing because it's clearly, oh sorry, that's increasing. Oops, this section is decreasing because it's going down. In this parabola, this one is going down, so that's decreasing. There's a straight line that's decreasing. Okay. And then we talk about concavity. So they give a different definition to concavity to normal, and they say a function is concave up if every chord lies within the function. Now that's true and it makes sense, but we can still think of it as like smiley. So if you draw a concave up function, the idea is you pick any 2 points you like and you join them up, and the chord is entirely within the function, right? So theoretically I could do there to there and join them up, and the chord is entirely within the function. So this is concave up, and a straight line has no concavity, but I could do a cubic, and anywhere to the right of the inflection, which is there, if I pick 2 points and join them with a chord, it will lie inside, so it's concave up over there. Whereas if I try to go, you know, from here to here, it's not inside, so the concavity is not always concave up there. It might be concave up for part of it, and it clearly is, but not for all of it. And then it's concave down if every interval lies within, sorry, I didn't use the word above, did I? Uses lies in, but it's below. Same idea. Doink, doink. And anytime you leave the curve, that's when you know concavity must have changed. So over here, this chord between here and here, concavity changed somewhere in there because the chord left the function. Okay, draw out, hit Kookaburra Valley, blah, 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 blah. So it just says, use the graph to describe the behavior of the river height. Well, the river height was going down, obviously. And it says what happened just about here. Well, my guess would be rain, probably, right? Because it's the rate of decrease has flattened out. So it started, you know, it was decreasing and it started to rain, so it flattened out. So the function was decreasing, but it was concave up. So here it is decreasing at a decreasing rate. So that means it always goes down, but the rate at which it goes down decreases. Mathematically, that means the first derivative is negative, that's decreasing. And the second derivative is positive. That makes it decreasing at a decreasing rate. This is basically like, think of it like velocity and acceleration. So this is a car going backwards but being pushed forwards with acceleration. So it's going backwards at a speed. The acceleration is in the opposite direction, so it's slowing down. Okay. And then over here, this is decreasing at an increasing rate. So mathematically, oops, the first derivative is negative, and so is the second derivative. So both the change and the change of the change, which is the second derivative, are acting in the same direction. Okay, so in other words, it is increasing. So you can extrapolate that out. So if you want a function that is increasing at an increasing rate, well, that would look something like this. And that's first derivative positive and second derivative positive. Okay, so again, the derivative and the second derivative are in the same direction, so they support one another. So I'm telling you this now because I want you to know that second derivative being positive doesn't mean it's at an increasing rate or a decreasing rate. It's whether they act both positively or both negatively or against one another. And again, think about the velocity and acceleration analog, which is to say this one is something moving forwards and also getting pushed forwards. So it's obviously going to be speeding up. Okay, so here we have basically that in a table form if you want to write it down. I don't know. I think the idea of the first derivative and second derivative is a bit clearer. But I suppose fx is increasing. I'll write this out in a second because it's going to get messy otherwise. First derivative is 0. Fx is decreasing. First derivative is less than 0. And then this is the second derivative bit. Oops. Okay, so it's the same idea. You really want them acting in the same direction. And then you really need to be able to take a sentence like this and then draw something to show that. So increasing at an increasing rate, always going up, and getting steeper as you go on. Increasing at a decreasing rate, I always think of as like an exponential with a negative power. So it's always going up, but the rate at which it's going up is slowing over time. Decreasing at an increasing rate, always going down and getting steeper. Decreasing at a decreasing rate, going down but getting flatter. And just to evidence again, first derivative is negative, going down, second derivative is positive, concave up, so getting flatter. So describe the branches of this function. So everywhere, it's got negative derivative going down. Over here on the left, it's concave down. And on the right, it's concave up. So the blue one is decreasing at a decreasing rate because it's going down. So it's decreasing, but it's slowing the rate at which it's going down. It's concave up, so it's at a decreasing rate. Whereas the green one is decreasing at an increasing rate because it's going down and is concave down. So it's moving backwards and it's being pushed backwards as well. Another important concept that we've also talked about quite a bit is the concept of an average rate versus an instantaneous rate. So an average rate is just something taken over time, like over here. Why did that not work? So the idea, must have hit okay. The idea is that you just take a start point and an end point and work out the rate of change that it implies. So an example is like, I'm running from here to here, and this distance is 100 meters. And you, for some reason, don't want to look at me because you're mad at me because I made you do too much homework or something. So you're facing this way, and you tell me to start, and you tell me to tell you when I stop, get to the other end, and you'll stop the timer. So, I'm feeling frisky, so instead of running in a straight line, I do this. whee, you know, and I actually cover 200 meters, and then I tell you to stop. And that might take me, 20 seconds because I'm a pretty fast runner, as you can imagine. And so you would say that the average rate of speed through that period of time is 200 meters in every 10 seconds. Sorry, 100 meters every 10 seconds, so 10 meters per second. Because as far as you're concerned, I only moved 100 meters. But in actual fact, my instantaneous rate of change on average was 20 meters per second because I moved 200 meters. Okay, that's basically the idea. In maths, we almost always talk about instantaneous rates of change, and we do that through the derivative, and we evaluate it at a point in time. That is the instantaneous rate of change. This is the average rate of change. It's rise over run, basically. It's the slope of a line, because as you can see here, you basically do it by drawing a chord over the top of your function. Okay, and remember the gradient is, the instantaneous rate of change is the gradient of the tangent. So let's try working through this example. Here's some work to do later. Okay, so avocado manufacturing, so very modern here with all the millennials and their avocado eating problems. So price and time is in months. Initial, so time is 0, price is -4 cubed, minus 12 lots of 4 plus 100. They have a negative initial share price. Oh, 12 lots of 0, come on. 100 minus 64, $36. Final. So 8 months, so t equals 8. Don't forget to go through the problem. Actually read it. So that's positive 64 plus 96. So what's that? 30. Sorry, minus 36. That's 96. That's minus 32 plus 100. So that's 68. So I got the calculator out. Me. So what was the rate of change of the price and the rate of change of the rate of change? So the rate of change is the P to T. So 3t minus 4 squared, times 1, but we don't need that, minus 12. So that's it. And then the rate of change of the rate of change is the second derivative. So that's 6t minus 4 to the power of 1. Again, times 1 for the chain rule, we don't need it. So when was the share price at a local maximum or minimum? So second derivative is 0, and what rate values will get there. So therefore 3t minus 4 all squared equals 12, just moving the 12 here across. Divide by 3 equals 4 square root. We need both plus or minus because then we're going to add 4. You've got to be really careful here. This is not plus or minus 6. It's 4 plus 2, which is 6, or 4 minus 2, which is 2. If you did plus or minus 6, go away, punish yourself, come back. No chocolate allowed until you get something right. Second derivative. So let's do t equals 2 first. So that's 6 times 2 minus 4, less than 0. Therefore, smiley, therefore minimum. And the price is just going all the way back to the start. I'm just going to do this in my head. So minus 8 minus 24 minus, why is it going to be bigger than 36? Maximum minus 8 minus 24, that's minus 32 plus 100, that's 68. Now, this goes back to something that I remember talking with Jamie about. This is a relative minimum, okay? Notice that it goes back, maximum. Notice it goes back to 68. That's even going to get higher from there. So it's a relative minimum, not necessarily a global minimum. And then t equals 6. the second derivative is 6 times 6 minus 4 greater than 0. Therefore, smiley, therefore minimum, much better. So P equals, so expect it to be smaller than, oh no, we don't necessarily. It's a relative minimum. So T equals 6. So we get 8 minus 72 plus 100. So that's 28, 30. Oh, it's 36 as well. How strange. They obviously pick these numbers very carefully. So it's a relative minimum. Again, it's not necessarily the global, because it's a relative. And basically what we've got here is they've asked us to draw a cubic function. And we've basically just shown that cubic looks like this, where that's 8, and that's my 68. And that's 6, and that's my 36. So that's what the cubic function looks like of the price, basically, over time. And that's what we've just proven. Now it says it actually stops at 8, so theoretically we shouldn't have actually drawn past there. And we shouldn't really draw past here either, I suppose, because it's time, but it's obviously easier to draw the whole thing and then delete. Find the points of inflection, sketch this curve. Well, I've already sketched the curve, but I'll add the inflection point, I suppose. So the second derivative is 0. Therefore, T equals 4. And when T equals 4, the price is 0 minus 48 plus 100, 52 schmackos. 452. There's my beautiful third of a page sketch. Describe the behavior of the price in different intervals of time using the terms in box 12. Okay. So basically, I'll do some highlighting here. So yellow highlighting, I'll go back. Oh man, this is going to be painful. Yellow highlighting is increasing at an increasing rate. So that's here. Okay, that's increasing at an increasing rate. Over here is increasing at a decreasing rate. Okay. And we'll use a green, and the other one I'll just leave unhighlighted, otherwise it's going to get very ugly. So decreasing at an increasing rate, so that means going down and concave down, so that's that little bit there. Okay. And it says find the average rate of increase. Well, that's just what did the actual price increase by, which, what am I up to, F, which from earlier was 68 to 36, and then it took 8 months to do that. So 68, yeah, okay, so what's that? 32 divided by 8, so 4. $4 per month. Okay, video number 1 down. You get to hear my voice again soon. Bye-bye.